Hello everyone, I'm Zoe Lim from KAIST. Today I'll be presenting our work, CLAY, Conditional Visual Similarity Modulation in Vision Language Embedding Space. This work is jointly worked by Lee Hyuk-suk, Jeongjun Park, and Professor Tae-Hyun Oh. Let me start with the problem definition. In image retrieval, given a query image, the goal is to find similar images from a database, but humans don't always look for visual similarity in the same way. For example, given this dog image, one user might want images of the same dog species, while another wants images with the same background. This is the task of conditioned image retrieval, which aims to retrieve images based on a user-specified text condition. To formalize this, we categorize conditional similarity computation into two forms. In the symmetric form, both the query and database images are conditioned on the text. Then, the similarity is computed by measuring cosine similarity of embedded feature v_q and v_d. This condition-aware visual feature extraction of both query and database images gives high retrieval accuracy, but requires re-encoding the entire database whenever the condition changes, which is computationally expensive. In the asymmetric form, only the query is conditioned, and this incurs low computational overhead since database features are pre-computed and reused, but accuracy suffers because database features remain condition agnostic. Thus, we can find here is a clear trade-off, accuracy versus efficiency. In this work, our goal is to resolve this trade-off. We propose CLAY, an adaptive conditional visual similarity computation method that leverages the embedding space of pre-trained VLMs like CLIP without additional training, achieving both high accuracy and computational efficiency simultaneously. Here's how CLAY works. There are two stages of text condition subspace construction and conditional similarity computation. Let me explain text condition subspace construction stage. First, we generate condition-related text prompts using an LLM and encode them into text features. Second, since VLM embeddings lie on a unit hypersphere, we account for this geometry by mapping the features onto a tangent space via the logarithm map, using the mean mu_c as the reference point. Finally, we apply SVD on the mapped features and take the top k singular vectors to construct a projection matrix P_c that defines the textual subspace. With this condition subspace construction stage, we can compute conditional similarity within this space. Also, this pipeline can be extended to multi-conditional retrieval by generating multi-condition related prompts in step 1. In inference stage, we encode query and database images with the vision language model. Then, we align the visual feature mean to mu_c via an orthonormal rotation h, which bridges the modality gap between text and visual features without distorting intra-feature relationships. Then, we map the rotated features onto the same tangent space and project them with P_c. Finally, we compute cosine similarity within this textual subspace as our conditional similarity. The key insight is that database features only need to be projected once per condition, which means that no re-encoding steps through the network is needed. We also constructed synthetic evaluation dataset CLAY-EVAL, since no standard benchmark existed with various attribute annotations. It consists of over 7K object images with conditions category, subcategory, and color, and over 6.5K human images with conditions age, action, and background. Each image is annotated with multiple attribute labels, enabling both single and multi-condition retrieval evaluation. Next, we will show our experimental results. In terms of retrieval accuracy, CLAY consistently outperforms all baselines across 5 dataset groups: Stanford 40, Fine-Grained Classification, Clever 4, CLAY Object, and CLAY Human. Notably, even without any training, CLAY surpasses trained methods like GeneCIS and InstructionTune models like InstructBlip. The qualitative results also confirm that our method retrieves condition-aligned images far more accurately than competing approaches. Now let's look at the accuracy-efficiency trade-off. We compare retrieval accuracy and inference time per query, measured separately for the first and second conditions on a 100-image database. While MLLM-based symmetric methods like QN3VL and VLM2Vec improve accuracy over asymmetric formulations, their second condition latency is as high as about 12 seconds, since the entire database must be re-encoded. On the other hand, Clay achieves comparable accuracy to symmetric methods, with a second condition latency of only about 0.12 seconds. This advantage becomes much more apparent as the database scales. As shown here, symmetric methods scale linearly with database size reaching over 125 seconds at n equals to 1K. Clay's inference time remains nearly constant regardless of database size, making it highly practical for large-scale scenarios. Furthermore, TSNE visualizations confirm that Clay adaptively modulates the representation space per condition. Compared to clip-based model, our method forms clearly separated, discriminative clusters under action, background, and age conditions. To summarize, Clay is an adaptive conditional retrieval method that resolves the accuracy-efficiency trade-off by modulating the VLM similarity space via a manifold-aware textual subspace without additional training. It achieves high accuracy without re-encoding database features, naturally supports multi-condition retrieval, and comes with Clay EVAL, a new synthetic benchmark for comprehensive evaluation. This is the end of our presentation. Please visit our project page and feel free to contact me if you have any questions. Thank you for listening.